Great. So thanks for having me. This is a very nice event, and thanks for including our paper. This is a joint work with Jose Luis Cruz, who's a student here at Princeton, and it's called the Economic Geography of Global Warming. And the idea is to propose an assessment model for global warming and the effects that global warming are going to have on the economy that is has geographic detail. So in order to do that, we want to take into account the three main characteristics of global warming that we think is important to incorporate in such a model. First of all, that it's a protracted phenomenon. It's a phenomenon that is going to happen over many years, and it's going to evolve over these years, dynamically. And so we need to have like a dynamic economy that incorporates these kind of slow-moving phenomena. Then it's going to be global in the sense that it's a global externality, as we all know. Emissions that happen in a particular place, quickly mix in the atmosphere and affect everyone. But then the effects on the different locations are very heterogeneous. They are heterogeneous because the actual temperature effects are going to be very heterogeneous, but it's heterogeneous also because the local effects kind of on the local economy are going to vary depending on the characteristics of those local economies, one of which is of course the temperature in those local economies, but also the type of things that they produce, the density of those places, etc. And so recognizing this heterogeneity is very important, and it's something that we're gonna highlight in this work. And we think it's important to highlight this because it's important to, in general, kind of the whole progression of economics and economic modeling has been about incorporating behavioral responses to shocks and kind of enriching those behavioral responses. And so this is something that has to happen also in climate assessment models. And so part of that is recognizing that it's affecting many different regions. And because it's affecting different regions differently, agents are going to have the ability to adapt by moving across regions, investing differently in these different regions, and trading across regions. So these are three important dimensions that we want to kind of incorporate in this assessment. Okay, there's kind of a long literature. This is a short presentation, so let me not go into detail here, but I mean, it's sufficient to just say that we're essentially marrying like a spatial economics literature that has been kind of developed in the last couple of decades with, the climate literature. Okay, so I'm not going to go over all the details of the structure that we propose to do this, but let me try to kind of summarize it with this diagram, what we do in this paper, and then I'll go into a few of the details. So the core of the economic model that we use in the paper comes from this paper with Klaus Desmet and David Nagy, and that paper proposes a spatial growth model. And in this model, there's different locations. Agents live in a location, they work there, there's land there. They work in firms. These firms are going to produce particular varieties of a good that they're going to be able to trade with others. And these firms have the option to invest in the local technology, to improve the local technology. And it's this purposeful investment that generates growth in this setup. And this growth is kind of important. We think it's actually quite relevant because it's what allows this economy to invest in new locations, right? So if suddenly Siberia gets warmer and people move into those regions, we want to give agents and firms the ability to invest in those regions, improve them, and make them more productive than they currently are. So we don't want, and this is, when we're thinking about hundreds of years or a phenomenon that evolves over hundreds of years, these type of investments are we think crucial when incorporating this type of investments is crucial. Okay, so these firms are going to have this ability to invest. That's going to affect the local productivities, which in turn determines wages and rents, and that together with local amenities, which determine how nice it is to live in that location, determine how the utility of agents in a particular location, and agents are going to evaluate the different options that they have, these different levels of utility that they can get in different areas of the world, and are going to, make the decision of where to live, or, whether to stay where they are or migrate somewhere else, subject to some migration costs. Okay, so that's the core of the model that we proposed in that previous paper. That's in some sense the dark part or the black part in this diagram. What we're adding in this paper is we're adding everything that is in green. So what is it that we're adding? We're adding another factor of production, which is energy. Energy in turn can be produced using clean energy or fossil fuels. The part that is produced using fossil fuels generates CO2 emissions. The CO2 emissions, through a carbon cycle, affect the stock of carbon in the atmosphere, which in turn affects global temperature. So we're going to borrow like a standard IPCC carbon cycle to do this part, which in turn then through a downscaling model implies changes in local temperatures. And it's these changes in local temperature then that affect the economy, the local economy. They affect productivities, they affect amenities, and they affect birth rates and death rates, and the difference between both we're going to call natality rates. Okay, and so they affect how many people, like population growth at the different locations. Okay, and then and so that kind of determines the effects of temperature on these kind of three key dimensions. And then we're going to take this model, we're going to quantify it at the 1 degree by 1 degree resolution, which is about 100 kilometers by 100 kilometers in the equator. Depends on, the latitude, the actual size of the squares, of course. We're going to use data on population and income. The baseline year is going to be 2000. And we're going to do like a standard inversion of this model to obtain the levels of amenities and productivities that rationalize these levels of population and income. And then we're going to use transport costs and migration flows such that the model, produces a standard gravity equation on one hand for trade flows and for migration costs, so that it exactly rationalizes the changes in net population at this level of disaggregation. So that's going to give us the migration cost. And then given that, we can run the model forward and obtain predictions for the world economy. Okay, so let me just give you a little bit more of that detail. So this is, think about the utility of an agent that has a particular history of where she has been, and today is at some location R. And this is the period utility of that agent. So that agent is going to get utility out of consumption, out of local amenities B. There's going to be idiosyncratic amenities as well, epsilon, the particular extent to which that person likes this location. And then there's the migration cost, the last term there. Temperature is going to affect utility through that green term B. And so those amenities, those are kind of, is a local characteristic. And this local characteristic of how nice it is to live there depends on congestion, which is this term here. The fact, so if a lot of people live in that location, gets congestion, people may like it less, to the extent that this parameter lambda is positive, which it will be in the quantification that I'm going to show you. And then what concerns us today in particular is the fact that that B bar then is going to be a function of temperature and changes in temperature. So that's this term here. So we're going to introduce this function lambda, and this lambda function is going to depend on the level of temperature and the change in temperature. So changes in temperature, say increases in temperature, are going to affect the different locations differently depending on the level of temperature on those locations. And that's how temperature is going to affect amenities. Okay, so Then temperature is going to also affect the, like I said, natality rates. That's going to be very simple. There's going to be a natality function here, n, that is just going to multiply the people that decide to live in a particular location, is going to tell us what's the population next period in that location before people make mobility decisions. And that function n is going to also depend on temperature. It's also going to depend on income in order to incorporate like a Beckerian quality quantity trade-off. I'll show you that that function in a little bit. Okay, and finally the production side. So production is a little bit more complex. So think about output per unit of land in a particular variety omega at a particular point in time and space, T and R. And so this is all importantly per unit of land already. And so land is an input in production already. We share 1 minus mu. And then you have labor per unit of land, and you have energy per unit of land. That are the two other inputs of production. And then you have the productivity part here. Part of it is like this purposeful innovation that we were talking about. So that feeds a decision for the firm. And then there is the productivity rho z, which comes from a distribution that is going to be, you know, as is standard in this type of model, like a Pareto distribution. But the level of that distribution is given by A, and this A is where what temperature is going to affect. So A, you know, is affected by agglomeration effects, potentially like knowledge spillovers, that type of thing. But on top of that, is going to be affected by temperature through a function, lambda A in this case, that has kind of, you know, similar features than the one for amenities that we discussed a minute ago. And then, you know, the past innovations are shifting kind of the frontier from which firms are drawing through, and so that's where growth comes from, and that's this part. Let me leave it at that for now. Okay, so those are the three key area or parts of the model in which local temperatures are going to play a role. One part that is important in the model is, you know, the production of that input energy, right? So that input energy is going to be produced using fossil fuels and clean energy sources, and we're going to aggregate that using this CES production function. And so, you know, you have fossil fuels, clean energy, and then there is an elasticity of substitution, epsilon, and this epsilon, of course, is important, right? Because, you know, how the extent to which we can substitute across energy sources is governed by that epsilon. Now, there's the price of these two sources of energy is going to be given by these Qs here, and it's going to have two components. One is just technological progress, so the price of extraction or production of clean energy is going to evolve over time. It's going to evolve over time, you know, at the same rate as the global technological frontier, which is endogenous, determined through the process that, you know, we discussed a moment ago. And then for fossil fuels in particular, there's going to be another component, which is that, you know, the more you use fossil fuels, the deeper you have to dig, if you will, and so the more costly is it to extract. And so that's this kind of top component here. So you have like a technological progress, which is the part that is dividing, that you have both in clean energy and in fossil fuels. And then on top of that, you have like this cost of extraction, this F function there, that depends on the cumulative CO2 that you've used in the past, okay? And that function, I'll show you that function in a second. So, and then the rest, like the trade part, etc., is kind of standard. So let me skip that, okay? So the climate component of the model is, you know, if you use fossil fuels, then you're gonna, like I said, generate CO2 emissions. Those are gonna mix in the atmosphere. That's gonna lead to global temperature changes. You know, we're gonna use the IPCC 2013 version of that, And we're going to focus on this kind of relatively, or not relatively, extreme scenario RCP 8.5 for the parameters of that model, okay? And then the key part of it is, well, how do you go from global temperatures to local temperatures? And there we're going to use this paper by Mitchell that says, well, you know, this linear approximation with kind of a local downscaling parameter is a good approximation. We've done different versions with you know, nonlinear terms there. They don't matter that much. But the key is this G. So this G tells us, you know, for 1 degree change in global temperatures, how much do local temperatures change, okay? I think I have it here. So this is the temperature scalar. We're going to estimate it using many local characteristics. And, you know, you can compare this with what others in climate models, etc., generate. It seems, you know, in line with that. And so what this is telling you is, well, a 1 degree Celsius increase in global temperatures is translate into changes in local temperature. To how big are the changes in local temperatures, right? So what this is saying is, in these northern latitudes in Siberia or Alaska or northern Canada, 1 degree Celsius increase in global temperatures translates into 2 degrees Celsius, an increase of 2 degrees Celsius in those areas, while in areas like in Central America, Argentina and Chile, Southeast Asia, parts of Africa and Australia, it only translates into half a degree increase. Okay, so big heterogeneity in how 1 degree Celsius translates into local temperatures. And you can see the kind of the resolution of the analysis that we're gonna do. This is the 1 degree by 1 degree resolution that I was discussing before, okay? There's a whole quantification here that I'm not gonna really go in detail or they're gonna describe in detail. The only thing that I'm gonna say is the elasticity of substitution, which again is important to think about some of these policies. Is going to be 1.6, which is kind of on the high side, if anything, we think. But you know, you can also think about this as an endogenous policy parameter. We can have that discussion if you want at the end. We're going to keep it fixed at 1.6 for now. Now, this extraction cost function that I mentioned before, it's going to be, you know, convex in the sense that it's more and more costly to use carbon the more you've used, and eventually it kind of asymptotes once you kind of use it all, if you will. So we're going to follow this paper by Bauer, that gives us those green points, and we're going to fit that curve that you see, the black curve, and that's going to be our F function. And this is going to come back, and it's going to be important later on, and I'll point to it. We are gonna, and so one of the key components in the quantification is those damage functions, those lambdas that I mentioned before. And so we're gonna use these functions here to estimate it. And so the way we're gonna do it is as follows. First, we're gonna do this inversion of the model. So the inversion of the model allows us to go from, you know, local income and population to local amenities and productivities for a given year, and then we can do that same exercise for different years, right? Do that inversion in different years, and so that's going to give us a panel of productivities and amenities at the local level, and in particular, it's going to be a 4-year panel over a 20-year period, or 4-point panel over a 20-year period for those years that you see there. And importantly, this is on the fundamentals already, right? So this is already taking into account all these mechanisms that the model has on trade and migration and investments, etc. So we're already kind of, in some sense, taking that out, which is something that we think is a good thing to do. And then you can estimate these damage functions, essentially get these semi-elasticities by temperature bin. And so these semi-elasticities are telling you, well, what's the effect on amenities, say, of a change in a 1 degree change in temperatures in a location that has this level of temperature, okay? And so we're gonna get one of these by bin, and we're gonna introduce local fixed effects, local trends at a slightly more aggregated level. I think these are by the 2x2 level in order to deal with kind of local characteristics, okay? And so this is what you get for this damage function. So these are these semi-elasticities. And so what is this telling you? It's telling you on the x-axis, I have the January temperatures for the Northern Hemisphere, July temperatures for the Southern Hemisphere, so winter temperatures, if you will. And what this is telling you is in the coldest places in the world, a 1 degree Celsius increase in temperatures increases local amenities by about 2.5%, right? And then, you know, as temperatures get warmer, this kind of goes down, and eventually it switches sign. And for the, you know, hottest places in the world, you get a decrease in 2.5 degrees. So if you get a 1 degree increase in local temperatures in the hottest places in the world, then amenities go down by about 2.5 degrees. So it's kind of symmetric as you can see it. And the optimal temperature is whenever it crosses 0. Okay, the same, we can do the same for productivities, and then you get the estimate, or like the curve or the estimates on the right. So what this is saying is a 1 degree Celsius increase in temperatures in the coldest places increases productivity by about a little bit less than 10%, while in the warmest places, it decreases it by about, you know, a little bit more than 10%. Okay, and now one of the things that you can see from this is, you know, this is kind of precise enough to have some significant effects in the kind of for extreme temperatures for sure, both for amenities and for productivities. But you know, there's a lot of uncertainty about exactly the level of this curve. It's not that we know exactly where this curve is. And one way to see that is look at, you know, the 95% interval or the confidence interval for the optimal temperature when this kind of crosses 0. And so that's pretty wide, right? So we don't really know exactly what kind of the optimal temperature is for production, but we do know kind of that you know, in the extremes, in this extreme is positive, in this extreme is negative. And so I'll come back to what that implies. And then finally, the natality rate, we're going to estimate an effect on temperature and the effect on GDP, like this Beckerian thing. And for temperature, we're using this paper by Cruz. Okay, so that's all I'm going to say about the quantification. And so let me show you some of the results that we get, and then I'll finish with some points. Okay, so this is, I'm going to show you, I'm going to run the model for 4 centuries, so from 2000 to 2400, and this is the first graph here on the left is the evolution of the CO2 emissions. And so you can see, you know, and then I have for you to compare 2 IPCC scenarios, the 8.5 one that I told you, you know, where was kind of, we were basing our carbon cycle on, and then the RCP 6.0. And so you can see that, you know, the run-up in the model of CO2 emissions is similar to the RCP 8.5. Then in these scenarios, what the IPCC says at some point, you know, you stop emitting, and then there's an abatement technology that kicks in. We don't have that in the model, but so you know, it's all endogenous to the economy, and so you know, it keeps growing, and then at some point it starts declining. Why does it start declining? Because this F function that I mentioned before, the fact that carbon and carbon extraction becomes more costly the more you've used, right? So you kind of have to dig deeper, and so that makes carbon more expensive, which decreases its use or makes people substitute towards clean energy. And so that's so it's in some sense endogenous abatement or endogenous substitution, I should say, generated by the model. And so, you know, by 2400, you've essentially kind of used the carbon out there, okay? And so that implies, of course, increases in global temperatures relative to the pre-industrial level that are, very much in line with this RCP 8.5 scenario, which, by 2200 implies about an increase of about 7 degrees above pre-industrial levels. And like I said, I mean, this is kind of an extreme scenario. But the numbers that I'm going to show you are going to be based on that. But the model our model kind of, follows what the IPCC 8.5 model implies for global temperatures fairly close. Okay. So what does that imply for amenities and productivity? So let me show you that for 2200. So this is, on the left-hand side, amenities in the amenities that we'll see relative to a world without global warming. And so all the areas that are red are areas that are going to gain in terms of amenities. Everything that is in blue are areas that are going to lose in terms of amenities. And on the right-hand side, I have the productivities. And so, it's not particularly surprising. Amenities go, but you can look at the levels, right? So amenities are going to grow by about 40% in the most northern parts, are going to decline by about 15 to 20% in Central Africa, parts of South America. It's this area here that is the most affected. And, the richest areas in the world are not that affected, including the US, Europe, and Japan. The same is kind of true for productivity, although a little bit more extreme. So these areas lose about 50% of their productivity, and productivity doubles in the most northern areas. And that actually comes down a little bit more kind of south for productivity than for amenities. This is this average scenario that I have. In the paper we have, we studied the different kind of more extreme or less extreme scenarios. Then there's the effect on population and global total population and the distribution of population. This is the implications for global population in the model. And I have a bunch of scenarios, UN scenarios there, kind of the confidence intervals of the UN scenarios. So we're kind of there within those intervals. But the effect of temperatures on population is kind of small. It's about 30 million people. So you can kind of hardly see the difference between those curves, or you simply cannot see the difference between those curves, because 30 million people is just not sufficient to show in that graph. But the big effect is that, about 600 million people are going to change location as a result of global warming by 2200, according to this. And they, and where are they moving? They're moving to those northern areas. Where are they coming from? Mostly from Central Africa, India, parts of the Southeast Asia, and Central America and Brazil. Okay, so that's but there's a substantial amount of people that change location as a result of this. And so if you put it all together, what do you get? These are the welfare effects. So this is the impact on a person that is there today. So in 2000, right, what's the effect on the welfare of a person that is in that particular area today? And so you can see the range of costs between 15% gains and 15% losses. So the range is quite big. It's about 30%. And perhaps the more troubling part is that if you look at the places that are going to lose a lot from this, like I said, up to 15%, is these are the poorest places in the world, right? I mean, so it's very correlated with income today. And the rich countries, again, US, parts of Europe, Japan, etc., that are all in this kind of band of latitudes, right? They are not that impacted by this. I mean, the welfare effects there are relatively small. So here is on the right, I have like a distribution of the welfare losses, and you can see that it's like has two peaks, right? Two modes, and one is like the poor world, like the India, the Central Africa, parts of South America, like I said, that lose a lot, and then there is the rich world here like the centers of population in the rich world that, you know, don't lose that much. And so this is really kind of the two stories of this phenomenon. You know, minor effects for the rich world, and then, you know, some areas that can gain substantially from this, which are these northern areas that are very, you know, are not heavily populated today. And so, you know, not a lot of people gain from that. I mean, of course, everyone gains from the ability to move there in the future. And so that's all accounted for here. Overall, the losses are about 6.5% in terms of welfare today, okay? But we are very uncertain about the level of these losses. And that's kind of related to what I was saying before when I show you the estimates of the damage functions. You know, there's a big uncertainty about the level of those damage functions. We don't really know where the optimum is, or I mean, there's uncertainty, or the confidence intervals are large. So if we bring that, those kind of standard errors from those estimations for amenities and those productivities, and we filter that through the model, right, and produce standard errors of the predictions of the model, this is what you get. Right. And so obviously these are, you know, very wide, first of all. I mean, that's the first point. And so just these are, you know, aggregate effects. So think about in terms of welfare by 2200, what this is telling you is, you know, the 95% confidence interval tells us that, you know, maybe the costs are 0 at the aggregate level, or maybe the costs are 20% in terms of welfare. And so 95 confidence interval puts us somewhere there, which is of course very wide. The point estimate would be more of about 8%, or between 8 and 9%. Okay, but a wide range there in terms of, we're not really sure what the overall effect is. We know it's going to be negative, but you know, whether it's catastrophic 20% or, you know, or mild, you know, that's all part of that 95% confidence intervals. And that comes from the fact that we're not estimating those damage functions very precisely, partly because we just don't have that long of a history of these effects of temperature on the economy with detailed enough data where we can do this inversion. Okay, what we do know, on the other hand, is the range. And so the range, you know, this is for this is the distribution that I showed you before, but now for, you know, the low 95%, the high 95%, so worst case scenario, if you will, best case scenario, and the one that I already showed you. And the point of this is that the range of the losses for the different regions of the world, that doesn't change that much across scenarios. So what, you know, the distribution is not the same, it changes a little bit, but the range doesn't change that much. So we're much more sure about the range of the losses rather than the level of the losses, that 30% that I was talking about before. So we know that those parts in Africa, we know that those parts in India, we know that those parts in South America, those are gonna suffer in relative terms out of this phenomenon quite a bit, and that range we're more sure about. Okay, let me skip this. There's a whole decomposition of the role of amenities and productivity in the paper. Just in a nutshell, what we get there is that, you know, both are important and amount to about, you know, half of the effect, roughly. Now, when I started talking, I emphasized like 3 key adaptation mechanisms, and the, you know, reasons why it's also important to incorporate this spatial or geographic heterogeneity. And the 3 were migration, trade, and investment. And so in the paper, we do kind of an analysis of the role that these different adaptation mechanisms play. The one that turns out to be the most important is migration. So let me talk about migration here. So what you have on the left is the effect of changes in migration cost on the effect of warming on welfare. So this is like the diff and diff, right? Of with and without climate or global warming, with low versus high migration. And so everything that is red here are areas that benefit from low migration costs, right? And so obviously, you know, the northern areas here benefit from low migration costs because that allows people to migrate there, and that's good for those areas because it creates investments and economic activity there in the future. So that we kind of understand. Perhaps, you know, more surprising is the different effects that migration costs have on, you know, India and Africa relative, say, to Brazil or Australia, right? So for Brazil and Australia, higher migration costs are actually, you know, reduce the cost of climate change, while for Africa, India, and parts of China, you get exactly the opposite, right? Higher migration costs are negative for them. And so why do we have all of these places are going to be highly affected by climate change? But the difference is that in Central Africa, migration is kind of an escape valve, right? I mean, people there, you know, the place is getting poorer or will get poorer as a result of this. There's going to be higher population growth. That creates congestion, and the ability to leave and move to other places, you know, increases welfare in those locations, and it's an important adaptation mechanism. For places like Australia or parts of South America that are much less densely populated, you have exactly the opposite. What they want is to keep enough population in these places. What they want is not enough people to leave those places, because if everyone leaves, then there's no market size, or market size are not large enough in order to have investment or sufficient investments in those places. And so for them, high migration costs allows them to keep more of their population, and that reduces the cost of climate change. All in all, if you increase migration costs by 25%, you increase the cost of global warming, or welfare cost of global warming, by about by about 33%. And so, you know, that's a very large impact of increases in migration costs. In this particular framework that I'm showing you, trade or increases in trade costs actually have relatively small effects. And the reason is that all this trade is kind of trade in varieties. Climate is not changing spatial, the sectoral specialization. And so, you know, the trade shock, the trade flows are very spatially concentrated, and so is the climate shock. So I trade a lot with locations that are close to me, but you know, those locations are impacted by climate, by global warming in very similar ways than me. So that implies that trade is not a great way to adapt, at least, you know, in this form that we have it here. So the effects that you get are relatively small, that you can see in all these curves kind of lining up together there. And then, you know, innovation plays an important role there. Higher innovation costs, you know, make it are bad for northern regions. They're good for all the main losers for climate change. Kind of one effect that is interesting here is that, you know, the overall effect on the cost of climate is actually a little bit counterintuitive, because higher innovation costs result in lower cost of climate. And so why is that? Like and here you can see like the importance of incorporating all these geographic effects and the reason is that in the baseline scenario, one of the big dynamics of the world economy is that, you know, population and output are concentrating progressively in India and China, right? And this process is facilitated by this innovation and the fact that you can improve production in those areas. And so there is this flow. But in the future, those areas are going to be highly impacted by global warming. And so in some sense, you're kind of investing in all these areas, and then global warming comes and, you know, and hurts them. And so if you have higher innovation costs, that prevents that process from happening, and so lowers the overall cost in the future of global warming. And so you can see kind of how those effects can be relatively complex. Okay, so I have a few minutes left. Am I right? Okay, perfect. So let me take the last few minutes to talk a little bit about policy and what are the policy implications of this framework. Okay, so the first thing I should say is that, you know, obviously it would be ideal to take this framework and calculate what the optimal policy it would be in this framework. There's of course many different market imperfections in the model. There's agglomeration effects, there's congestion effects, and then there is, you know, the whole global externality that's coming from carbon. So there's also technology diffusion. But calculating the optimal policy, implies, sorry about that, implies solving a pretty complicated optimization problem that we don't really know how to solve. And so I cannot offer you the optimal, sorry about that, the optimal policy. I cannot compute the optimal policy. I don't know how to compute the optimal policy. So what I'm left in this model, so what I'm left with is trying different things out. And so I'm going to try different things out. The first one is carbon taxes, which of course are like a popular policy option that many people talk about. So just for you to get a sense of the policies that we're going to impose is we're going to impose a uniform policy everywhere in the world of a certain percentage tax on carbon. Here I have like 50%, 100%, 200%. To give you an idea, 200% is similar to the Swedish tax, 50% is similar to the EU emissions trading scheme. And so what does the carbon tax do? It lowers emissions, obviously, you know, at impact. Now, here this curve, this F curve that we talked about before, comes in, and it's kind of important because think about it, right? So carbon taxes reduce the consumption of carbon, but that means also that you move less up that F curve, that cost of extraction curve. And so that means that in the future, because you consume less carbon, the cost of extracting carbon is also going to be lower. And so that's a force that is going to operate kind of against the tax, right? And so what does that overall give you? It gives you that, you know, the carbon tax reduces carbon, you know, for about, what, 150 years or so. But then eventually you kind of move so much up the curve you don't move up the curve in that case. And so that keeps the price of carbon, the cost of extracting carbon, relatively low, which implies that eventually you switch. Eventually, with the tax, you're actually consuming more carbon, as you see in kind of these scenarios here. At the end of the day, you end up consuming most of it anyway. This is partly because of the type of technology to produce energy that I showed you before. And so what does that do? It reduces temperature. So here are this is the effect on temperature. Reduces temperature, and essentially what it does is like it flattens the temperature curve, right? So it reduces temperatures for a long time, you know, throughout, but you know, you end up more or less in the same place. It's just that, you know, the curve is much flatter, and so you lower temperatures for many years, right? So that's the main effect, that you lower this temperature for many years. So this has cost in the short run and benefits in the long run. The benefits come from the fact that temperatures are going to be lower, and that's going to encourage investments, and so that has like a growth effect. But you know, as is standard in this type of analysis, you have current losses, future benefits, and so, you know, evaluating this policy depends crucially on the discount factor. Here, the discount factor depends, you know, has to take into account the fact that the economy is growing, right? It's growing at about 3%. So a discount factor of 0.97 would essentially value future agents as much as current agents. If you really push that towards 0.97, then carbon taxes, kind of large carbon taxes, are the optimal policy. If you make it a little bit lower than that, then no. Okay. Now, as you know, the fact that carbon taxes are flattening the temperature curve and essentially delaying the consumption of carbon, of course, is very useful if there's an abatement technology that is forthcoming. So if eventually an abatement technology comes, the fact that you delay the consumption of carbon is great, right? Because you know, you eventually solve the problem. So a little bit like a vaccine coming. So lockdowns when a vaccine is forthcoming. But here is like you're flattening with carbon taxes the temperature curve. And then if the abatement technology comes, the fact that you haven't used all that carbon until now is very useful because you didn't increase the temperatures. And so that gives you an extra boost on the carbon taxes. So you know, the combination of carbon taxes and abatement technology, that's what can really be effective for this economy. Let me finish with clean energy subsidies. So you can also introduce those. In this framework, they actually are beneficial, but they have relatively small effects on carbon emissions and temperatures. And the reason is very simple. The reason is that given the parameterization that we have, they increase the total use of energy to an extent that at the end of the day reduces the use of fossil fuels very little. It obviously, in relative terms, shifts energy production towards clean energy, but it also increases the total use of energy. And so at the end of the day, those effects kind of cancel out, not exactly, but kind of roughly cancel out, which implies that you have small effects both on emissions and on temperatures, even though you have relatively large effects on the economy because it acts as a production subsidy, essentially. And because this economy, there's all these innovation effects that are not fully internalized, that's actually useful for the economy. But it's useful for the economy in some sense for the wrong reasons. It generates, it increases output growth, but it doesn't solve the emissions problem and the temperature. Okay, so let me stop there. Like I said, there's of course many other policies that one can do and can try out in this framework. Is constructed exactly for these purposes, and these policies that I've showed you are just kind of illustrative, mostly in nature. Of course, one can do very local policies, all sorts of different variations of this. And so, you know, I invite you all to try it and play with it. And so, just to conclude, we think that it's, you know, important to incorporate this spatial heterogeneity into climate assessment models, partly because it leads to important adaptation, and partly because it allows us to assess the effect that this phenomenon is going to have on the different regions in the world. And we think that this is really the main aspect of this phenomenon, the fact that it's going to affect these regions so differentially over time, and that at the end of the day is in some sense the key problem more than the average losses in some sense. And that because it's going to affect these regions so differentially across parts of the world, that's also going to lead to large adaptation, mostly through migration, partly also through changes in the places where firms and individuals are going to invest in the world. Thank you.
Perfect. Thank you so much, Esteban, for this very rich presentation. I'm going to invite Alba Patozzi, a PhD student at the Faculty of Economics here, to kick off the Q&A session. And then we also have a few other questions from the chat, and if anybody else has other questions.
Super.
Alba?
Hello. First, let me say thank you for this very interesting and insightful presentation. This paper certainly makes a rich contribution in the climate economics literature. I have two questions. My first question concerns the distinction between global warming and climate change. while rising temperatures are one outcome of climate change, there's other phenomena such as volatility in temperatures and extreme weather events, which are equally as concerning. I was wondering what the paper can tell us about the economic damages associated with, say, a higher volatility in temperatures in addition to their rise in levels. And my second question is on the uncertainty surrounding the timing and severity of economic damages associated with global warming. From the lens of your model, how important do you think uncertainty that households face would be in estimating the overall damage from climate change? In other words, how would climate uncertainty impact investment and employment decisions through risk aversion and other channels? Thank you.
Thanks for the questions. These are great points and issues, or important issues to consider. So we haven't really incorporated that either. I mean, not because we don't think they are important, but because we're kind of moving in steps, I guess. So the first thing is this distinction between global warming and climate change. I don't know that, I'm not sure that people have a very standard distinction between these two things. The way I use the distinction is, this is the effect of temperature, and then I can have the effect of sea level rise, which is also kind of the result partly of temperature, of course, but it's kind of in some sense, a different phenomenon that we've studied in other work. Now, in terms of the, particular events or that can affect economic activity in certain areas, like episodic kind of effects of climate change. I think there's two ways of thinking about it. One way, which is kind of in line with this type of framework that I presented, is, yeah, I mean, there's some frequency of those events. That frequency is changing, and I'm going to think about these damage functions that I show you as incorporating that on average, right, in those regions. So if a region is kind of more affected by all of this, that's going to reduce the amenities in that location on average. It's going to reduce productivities in those locations on average. And so, I'm incorporating this effect. We're looking at very long periods. So, the yearly frequency of the tornado in some sense is not what we care about. What we care about is the fact that those areas now are damaged because this is happening, right? So I don't really need to take into account those events one by one. Now, of course, you can think about, more longer term phenomena that affect the areas for some period of time, etc. Perhaps that is more important to incorporate. And so, you could do that if we had a good model. I mean, and maybe there is, and I just simply don't know it, from the science side that tells us, here is a good way to model that and to combine it with the evolution of carbon emissions, etc. You can incorporate that. There's no particular problem. We've done that for flooding, for example, because we did have like a model of flooding and kind of a stochastic in some sense, or probabilistic model of flooding that, Oppenheimer and Cobb gave us. And so, we use that in some other work. The other component or part of your question that I find interesting is this uncertainty, right? And the role that this uncertainty about this can have. And so have agents that take into account the uncertainty of these outcomes across regions of the world, etc. And so, I think incorporating that would be interesting. It's not an easy thing to do because, modeling agents that have like these consumption savings decisions within these frameworks, it's hard. So that requires kind of like a methodological innovation of how to incorporate agents that have that actually face those trade-offs, and therefore evaluate these different paths as as risky as risky paths. So right now, the only asset price that is really affected by the evolution of climate and the potential uncertainty in the evolution of climate is land prices. But land prices in the model that I showed you are not allocative, right? So, and so in that sense, they don't affect the outcomes in this economy. You would need to make land prices allocative. So for example, if you start bringing in financial frictions or things like that, that of course would make them allocative, and then suddenly you have that channel. But again, that brings in the complications of having these forward-looking agents and dealing with those forward-looking agents in solving the model, which is not easy. So there's some methodological issues there that need to be solved before we can actually do that properly. But you know, it's we're trying.
Richard Toll has a question too.
Hi, Esteban. I expressed my admiration for this work previously, so I won't repeat that now, but I do have a question. And I was a bit surprised that you talked about welfare and just talked about as if it was non-problematic. Now, welfare is a problematic concept, or social welfare, the aggregate utility across people is a problematic concept. Always, if we have a constant population, it becomes very ropey when we have changing number of people, but typically in this literature we just brush over this. But you have endogenous population. Through your policy measure, you can create additional people, and definitely through policy measures, you move people around. So I really wonder, how did you define welfare in this case?
Yeah, so that's a great question. Thanks for it. And thanks for your comments on the paper. I mean, I'll tell you what we did, and then I'll tell you, you know, what is the, I mean, this is like a philosophical issue, right? Almost, or not almost, it is a philosophical issue. The welfare measure that I showed you is what is the welfare of an individual that is alive today, living in that particular location. That's what I'm giving you, right? And so I specify the preferences of these individuals, and this is like a dynasty, like a guy that is living, you know, his life and forever, and is moving, potentially doing whatever, you know, it's optimal for him or her to do, but it's today alive in that location, right? Now, and so it's a per capita measure in that sense, right? Now, there's going to be other people that are going to be, you know, are going to be born in 100 years that are not in that calculation, because exactly this is a per capita measure. But when I do the overall welfare, I do take into account that they are going to start obtaining utility, right, at some point in 100 years, right? So that's the mechanical way in which we do it. Now, of course, as you correctly said, I mean, these policies that we're putting in place, right, are affecting the size of population in the future, and not trivially. I mean, I show you that like climate change is like 30 million, so that's, you know, maybe in the rounding error for parts of it. But once you go to other policies like these carbon policies, or changes in migration costs, or changes in trade costs, etc., those changes in population can be much more substantial, partly because of this Beckerian mechanism, right? Because poverty affects the number of children that people have. And so what that implies is that, you know, these per capita measures of welfare, in some sense, like the welfare of an individual, in some are missing something, because, well, maybe everyone is a little bit less rich, but we have a society that is larger. How do you make that trade-off? And that, I think, is the key question, right? And we are, and the short answer for this paper is we're not, because we're keeping this kind of per person kind of welfare measure, and that's in some sense the correct. But I agree that it's not obvious that that's the correct one, in the sense that policies that actually increase population sizes in the future, you know, can be desirable policies as well, or policies that reduce population are not necessarily very ideal policies, even if they make the people that are gonna, you know, be alive better off. But even with those challenges, we think it's important to incorporate the population growth because, if you think about it, like the role of a person that moves today from Central Africa in terms of carbon use and the implications for climate from Africa to Germany, right? Yes, that person today is going to consume more in Germany, probably is going to, generate more carbon emissions, but through that Beckerian mechanism, the dynasty that is going to come out of that person is going to be much smaller, right? And so you have to take that into account also in terms of future emissions and the future emissions that generates. Just to keep it short, I think that's a crucial question in how do we evaluate these policies. I don't have a great answer for this is the right way of doing it. The only way that we really have is to incorporate children, I think, into preferences and do it from today's individuals, from the perspective of today's individuals. That's the only real anchor that we have to do this. The rest is obviously we can impose a social preferences on this, but we can obviously disagree on how to do that in particular.
Thank you so much, Esteban, for all the answers. There's a few more clarifying questions in the chat, and there's a couple of more hands raised, but unfortunately we have to move on to Felipe's presentation, but there's a general discussion in the end, and all of these questions can be revised.
Great, thanks so much to everyone.